I want to briefly talk about what this chapter is all about. And it's about having two variables and trying to figure out if there is a correlation between them, a relationship where changes in the one variable is going to affect and change the other variable in a way we can measure and predict and make intelligent predictions about the future. So here's a few examples of things you could gather data about and then try to find a linear correlation. One could be the caribou population in Alaska, and you're trying to see if the changes in this population is going to affect the wolf population in Alaska. So maybe as more caribou are born, the population gets bigger, maybe there'll be more wolves in Alaska because there's more food. And maybe it'll also be true then that as there's less caribou, there would be less wolves because there's less food. So you could gather data about that and see if there's a linear correlation. Business, you could try to compare the number of TV ads a business is putting out to their total sales. More ads you're hoping will lead to more sales, and less ads would lead to less sales. So these were both examples of stuff we would assume to be positively correlated, where an increase in the X is going to lead to an increase also in the Y. So more TV ads, more sales, and vice versa. Less TV ads, less X is going to lead to less Y, less sales. So that's positive correlation. There can also be negative correlation where you do more X, so more hours spent in safety training, you would assume that would lead to less total number of accidents at work. So as X gets bigger, you do more training, there's going to be less accidents. This is a negative correlation. If X is small, you do less Y, then there's going to be more accidents. So they move in the opposite direction. And then there can also be times where a statistician's looking for a relationship between two variables, but one just doesn't show up. There really is no correlation. So like a person's height to their retirement age, there's probably no correlation at all between that. Taller people don't retire earlier, shorter people don't retire later. It's just random. Height has nothing to do with retirement age. So visualization, page 139 has some great pictures to kind of wrap your head around this. If you get a whole bunch of data, so your X values and Y values, and you make a scatter plot, and it looks like this would be like the height and retirement age. There's no real pattern. It's just all over the place. You can't predict someone's retirement age based on their height. These rarely ever happen in the real world where you have a perfect straight line. What happens more often is you gather data, let's say about the caribou population or the TV ads, and you'll get a scatter plot, and then you find the line that best fits that scatter plot. It's closest to as many points as possible. And then you can use that line to predict. So it's going up. This is a positive correlation. The slope is positive. So as the caribou population increases, the line's higher, and you expect the wolf population to be higher. Or the X could also be your TV ads. As your TV ads increase, the line is higher, and you expect your total sales to be higher. And then here's a negative correlation where you've gathered a bunch of data about, let's use my example of hours spent in safety training versus work-related accidents. So as your hours spent in safety training increases, you see the line going down. The number of accidents is going down. So the Y values are getting smaller. So for the homework problems here on page 167, number 2 requires a little critical thinking. Read through it after you read the chapter and give your best answer there. Number 4, I highly encourage you to do the Excel assignment first. The Excel assignment is very similar to number 4 on page 167. You'll learn how to use Excel to answer number 4 in almost its entirety. And so do Excel, become familiar with it, and then go back to number 4, and you should find it pretty easy.